Hey guys, welcome to another exciting C++ algorithms tutorial video. In today's video, we'll be generating some random noises using Perlin noise algorithm, which is actually a very interesting algorithm proposed by Ken Perlin, and which generates gradient noises, a kind of noise which has some smooth values and a local cohesion between the values, and which can be used in different kinds of scenarios like terrain generations or different kind of texture generations in CGI industry or any kind of area where you need some natural random noise, some noises which has some local coherences. You can go with this Perlin noise algorithm. Now, as far as the implementation goes, it's a graphics related algorithm, so we will need a simple graphics oriented library. For that, I will be using olcPixelGameEngine. You can go to the GitHub repository of OneLoneCoder and you can download this file from here. So first of all, to download this file, I am just going to show you the easiest way. You go to that repository like I did here, and then you open this file here. You go to the raw and you select the whole thing and you copy this whole stuff, just pressing Ctrl plus C, and then in your favorite IDE or editor you create a new file. So in case of VS Code, I will just Visual Studio, we will just add a new item and just name it OLC Pixel Game Engine .h, and when you are done creating, just delete whatever inside is present inside that file and paste the whole stuff and hit save. Okay, press yes and it's done. The good things about this library is that it's a header only library, so it's a standalone library. You can just put it inside your project and it will work. You don't need any additional dependencies or stuffs like linking and those kinds of things. They're already done. And the second thing is this is cross platform, so you can also use this for Linux and other distributions. Even there is a web distribution available, I think, and it's very easy to use and stuff like that. So that we already have our library here, we can jump into our algorithm. And to have a brief overview, let's just look into this image here. So we will have our plane or our 2D plane. We will generate 2D Perlin noise for this demonstration. So our 2D plane will consist of some rudimentary points. We will call those points grid points, and this is the grid, which are integer indexes like 0, 1, 2, 3 and so on. And these 2D grid, they have these cells, and whenever we pick a point in this grid, it will fall into any of these cells. Let's say I pick a point here in this location, so it falls under this cell. Okay, this point falls under this cell, and each cell at these vertices of these cells, we will have something as some random direction vectors that will show a direction, and we will use these direction vectors and we will find distance to these points from our given point, and we will multiply the distance with these direction vectors to get the four estimated values for these 4 points, and then we will just interpolate between those values to find the value that we want for this particular point in our noise. The algorithm is like this, and it's actually very simple to implement. So just let me show you. So first of all, before we do any kind of things related to noise, let's just create a simple olcPixelGameEngine application. So I will first define olcPGE application. This is a macro that enables the header file. So you need to define this macro before you include olcPixelGameEngine. So you will include olc pixel game engine here. We will also include vector, and for random numbers we will just simply use our handy cstdlibs rand function. I think it's quite good for this demonstration. Now let's just have this controversial thing using namespace std. You can use std colon colon or namespace std. It doesn't matter. This is a single file application. I don't think anything will trigger the same names present in std library, so I am fine with this. And now just create our main function and return 0 from here, which is also optional, but it has been a practice, so let's return 0. Now to create a olcPixelGameEngine application, we need to define a class, whatever it might be. For this purpose I will just call it demo, and it extends or it inherits from olcPixelGameEngine. Now everything in olc, they are inside olc namespace, so olcPixelGameEngine, olcPixelGameEngine, and we will declare everything as public because we are not doing some high level stuff where we need encapsulations or stuff like that. So to create a olcPixelGameEngine, we need two things. First of all, we need on user create function, which is a boolean function, so we will append bool in front of that like this. And the purpose of this function is that we will override this function, which will be called at the beginning of the application. So let's just say override. You can also omit this keyword, it doesn't matter, and we will return true here because it's a boolean application, so true like that. And we will also need another function which will be called on each frame of that application, and it's called on user update. The names are pretty straightforward. It takes an argument called they called it elapsed time, I called it tt, it doesn't really matter. But all this variable does is it provides us with something called as a delta time, that is the time that has been elapsed between two consecutive calls of on user update, if I am not wrong. And this function I will also return true from here, so return true like that. And this is all about the demo. We can define some constant variables for our application, like define width 200 and define height height 200, and I can also define pixel size for both x and y. And now that we have this application, we can simply invoke this application by creating an instance of that application, so demo, and then we will check if the application is constructed successfully by calling demo.construct. So demo.construct, here we will pass width, height, pixel size for both x and y, so pixel size comma pixel size. Okay, and if the construction is successful, we will just call demo.start. So this is all about creating a simple olcPixelGameEngine application, which will give us a window where we can draw stubs to show the output of our Perlin noise. So as you can see here, we have this blank window here. We can use this window to draw stubs, and it's working fine. So now without further delay, let's create our noise class. I will call it class Perlin noise 2D because I am implementing a 2D version of the Perlin noise. and let's make everything public, because why not. We'll have a function called let's say init. So void init, because I don't want to use constructors for trivial purposes like this. So I think init will be fine. Init will enable us to reuse our same instance again and again. And also we'll have a float called value, which will give us the value for a particular given x and y coordinates. So float x, float y. Okay, pretty straightforward, right? So now that we have our this one class Perlin noise 2D, we can start creating Perlin noises. And for the first step, we will first create this awesome looking grid here. Okay, so for this grid of vectors, we need a class to represent vectors. As far as I know, they have a vector class here. I don't remember it, so I will just simply create a struct called vector. I call it vector because it's a two-dimensional vector, and it will have two floats, float. One is x for for the value of x-axis, and y for the value of y-axis. It's as simple as that. We'll also define a function which will be the dot product of two vectors. So we'll call float vec dot product. Let's call it dot product. So dot product, and it will take two vectors. So const vec 2 reference v1. It's very hard to type these things. And then const vec 2 reference v2, and here we will do some very simple stuffs like returning v1 dot x times v1 v2 dot x plus v1 dot y times v2 dot y. As you can see, it's already looking pretty damn simple thing. If you don't know what dot product is, you just go check some mathematics on vector, and I think you will understand. So the first thing that we need to do is we need to create this grid that we will be using as our reference. So I will have it as a member, so I will call it vec2 a vector. This vector stands for our vector container of vectors. Okay, these are our custom vectors, the mathematical vectors, and we will call this gradients. What a name. And we will also define a wraparound size. So hash define wrap size, WRAP size, which is 256, so that if we go out of the range, we will then come again, start again from 0. Whenever we exceed the value of x and y here in the value of 256, we will again start from 0. So for that we will use wrap size. So for each integer value of this x and y, we will have one gradient present. So first of all, we will have some choices between the gradients, and let's create some random gradients. So I will call this vec2 grad. It will have 4 choices to begin with, each of which is normalized vector. So we'll have these 4 vectors, so which are pretty damn easy vectors. One is 1, 0, one is 0, 1, one is -1, 0, and one is 0, -1. Okay, so these vectors, they essentially show the direction to each axis. This directs to x-axis, this directs to negative x-axis, this directs to y-axis, and this directs to negative y-axis. Now we also need to put a semicolon here to finish this vector, this grad definition. And now we will generate our gradients. So before we generate, let's reserve some space for our gradients. So gradients underscore gradients gradients, okay, dot reserve. And here let's reserve, we have wraps, we have this wrap size, which will be the size of cells present in x-axis and present in y-axis. So we will just say wrap size times wrap size, which is the size of our entire grid. Okay, ACRV. This is a wrap size, not heap size. So WRAP wrap size. So now let's randomly assign these gradients to our vector. So let's say gradient. So let's just create a for loop here. For int I equals to 0, I is less than this wrap size times wrap size. So wrap size times wrap size I plus plus, and then we will say gradients gradients I is equals to grad, and here we will call rand for a random index, and the index should be wrapped from 0 to 3, so 0 1 2 3. So we will just take gradient and for the index rand modulus 4. Now we will pass a seed here for the consistency, so we'll call this int seed, and let's give the seed a default value of 0, and at the beginning of the initialization we will just call seed, we will call srand using the seed value. Okay, so we will seed the rand, rand. Okay, so this is all about generating our grid. Our grid has all those points, those 256 by 256 points, and we can use those. So now let's get into the value gathering part. What we will do is a very simple task. First of all, we will separate the integer part and the fraction part from x and y. So let's say int ix for integer part of x equals to, we'll just simply cast x to int, and the same thing goes for y. So int iy equals to cast to integer y. Now for the fraction parts, we will take them as float, so we will call this fx, and it will be x minus the integer part of x, as simple as that, and float fy equals to y minus the integer part of y. Okay, and this will be float. Now first of all, for every point we need to get the 4 points which are surrounding that point in the grid. So the 4 points that represent to the points surrounding to that grid, and for that we can simply say that the gradients vec p, and before that let's wrap this ix and iy using wrap size. So ix equals to ix modulus wrap size, and this will be a single x. As always, I am having a lot of typos, and iy equals to iy modulus wrap size, like that. And so we have our initial variables that we need. Now all we need to do is we need to find the 4 cells, the gradients present in those 4 cells, like in this image, for the nearby cell and the nearby 4 vectors that will be used for calculating the gradient values. So first of all, let's have a vec3 vec, vec2 p top left, that denotes the top left corner, and its underscore gradients EIENTS gradients, and it will be y times wrap size plus x, because y times width plus x essentially means that we are considering the one dimensional as array as two dimensional array. Now we'll have additional four vectors, one for top right, and which will be for x plus 1, y plus x plus 1. So the next cell, for this is the top left cell and this is the top right corner of the cell, and then we will have also bottom left and bottom right. And for bottom right it will be y plus 1, because we are going one down to the y axis, and in this case we will be going to one down to y axis and one down to x axis. Okay, now for a simple visualization that we sometimes do, I will just draw here how it will look. Okay, so let's say this is our vector here, and we have this mark here. This is our point for which we are trying to find. So this is the y comma x, this is the x comma y point. Okay, let's call it. So this is our top left point, so this will be obviously x plus 1 comma y point, and this point here will be x x comma y plus 1 point, and as we can see this will be x plus 1 comma y plus 1 point. So these will be our 4 points that are surrounding our main point to the grid, and the vectors present in the points will be the values inside this gradient vector. As simple as that. Now we need to find the distance from these p points. Now as you can see, we have already eliminated the integer part from p, so we already have the fractional part. So for the distances it will become quite simple. This x will become 0 and y will become 0, because we have already subtracted the integer part from both sides, and this will become 0 comma 1, this will become 1 comma 1, and this will become 1 comma 0. Okay, as you can see. So just like same, we will create 4 distance vectors. So vec2 d top left, which will be equals to, we will use the initializer list to initialize fx and fy. Okay, so because we are subtracting this vector, this value from this, so from x we will subtract 0, from y we will subtract 0, and like the same we will subtract it for the top right and the bottom left and the bottom right. So the bottom top right corner, you can see that for x we will subtract 1, and for bottom left we will subtract 1 from y, and for bottom right we will subtract 1 from both sides. Well, just subtracting these vectors from this original our p vector, and that's it. So that we have the distances. Now we can find the values at each point. Okay, so for that we will just create the dot product, and I will call this so let's say float if top left equals to dot product of our p top left, the vector present in top left, and the direction vector to top left, so d top left, just like that. And we will have this for all the 4 points, so 4 corners, so top left, top right, bottom left and bottom right, and the values will be here same, so bottom left, bottom right, and this will be, this is bottom right and bottom right, sorry, this will be bottom left, and bottom left. This will be top right and top right. Okay, so we have top for the value for the top left, the value for the top right, the value for the bottom left, and the value for the bottom right. Now we need to interpolate these values. So for the interpolations, I will just simply declare a lambda function. I will call this auto, let's say lar. They call this function lar sometimes for interpolation, and it will take two float values. So const float reference a, and let's remove const here because it will take a little bit more space. Float reference b. Okay, and what this function will do is it will simply return us and also the amount uh, to in which we are interpolating. So we will call this shell float w. So the concept is this: if you are interpolating between 2 points, if and we are assuming that the value by which we are interpolating is between 0 and 1, so we will just multiply the distances from that point to those points, that very w value, in reverse order from with both points, and add them. So let's say so it will be like this: a times 1 minus w plus b. Okay, as simple as that. Now if you really don't understand what interpolation is, you can just simply google it. So you can search interpolation, and it's just finding the middle value between two values. Like if we are finding the value for the middle, then w will be 0.5. So we are just essentially adding a into 0.5 plus b into 0.5, which is a plus b by 2, which is the average of a and b. And when it's not the middle point but slightly shifted point towards the a, the contribution of a will increase. And so the for the greater for least value of w, the contribution of a will increase, because 1 minus w will be bigger. And for b times this will be b times w, by the way, not b, this is my fault. So b times w, and this will be a times 1 minus w. Okay, so if we see interpolation here, you can see that this goes something like this, but essentially it's the uh, linear interpolation. Let's search it. Linear interpolation, the thing we are doing is linear interpolation. So we can see here, if we search here, we can find all the things about the linear interpolation. So whenever we are doing linear interpolation, there should be that formula somewhere, which is just like this. Okay, that v times t, they are just summarizing this thing, because if we take t common from both side, it will look like this. If we take w common from both side, it will look like this. So if we take w common, so if we take w common, it will be uh, b minus a, and we will have a for 1. So this is these two formulas are essentially same, but in this case we are multiplying only once. In that case we were multiplying twice. So obviously this formula is better, so we are using that. And they are also calling it lar, because it stands for linear interpolation. And you can find a lot of explanation why it's happening. I'm not going into details. So we have this lar thing, and also we need to smooth the gradient, because for some reason there are some artifacts. So for this particular scenario, the Professor Perlin has also introduced a smooth function. I will be using that function. So we will call this auto smooth, and this one is pretty much thing to buy heart. You have just to remember these things, that this thing is this. If LOAT, there is no logic behind it, it just works. I can show you the curve. The curve looks like S, like this S, and all we need to do is we need to return a very weird formula. Let me just write the formula here, and then we will summarize that formula like what we did here. So the formula is 6 times t to the power 5 plus, not plus but minus 15 times t to the power 4 plus 10 times t to the power 3. So as you can see, this is a very weird looking formula, and for this we will first of all common t cube for both from every element. So we'll have t times t times t, and then we will have t times, for t square we'll have t times t times 6 because 6 has t to the power 5, minus 15 because it's t to the power 4, and we plus 10. Okay. So it will look like this, and these are the two functions that we need for our calculation, final calculation. So that being done, now we can just jump into our final calculation. So we will have our fx converted to smooth. Fx is the fractional part that we extracted here. Okay, so fx equals to smooth fx, and likewise fy will be smooth fy. Okay, and now that we have the fx and fy set, what we can do is we can just first of all find the interpolated value for the top and for the left, and interpolated value from the for the right. So we'll just say float if left is equals to lar, or linearly interpolate between f top left f top left and f bottom left using the y value, so fy, and samely likewise we'll find for a right, which will be for both the right values interpolated by the y component, and then we will find our final value. So float value equals to, we will once again interpolate, but this time on x-axis. So we'll have left here fl and fr right here, and we will interpolate by fx. Okay, so we have this final value, but this value will range from -1 to 1, and we need to convert this to from -1 to 1 to 0 to 1. So for that we will return value plus 1. So -1 will become 1 and 1 will become 2, and then we will divide by 2 to convert it from -1 to 1 range to 0 to 1 range. And that's essentially it. That's quite sufficient. You can change these values to 1.0 for 1.0 here and 2.0, and that's all about generating our Perlin noise. It's as simple as that. Now let's look into some visual representation of our Perlin noise class. So for that we will have our Perlin noise instance. Everything will be public, so per Perlin noise 2d noise, this will be our Perlin noise class instance. And for our little demonstration we will have some offsets to move around the noise. So offset x and offset y, and we'll also have a scale using which we can scale around the map. Okay, as simple as that. Now let's set these values. So offset x is equals to offset y is equals to, let's say 0.0 for the beginning of the map, and let's say scale equals to something like 2.0. Now for the purpose of movement, we will have a float delta value, float float delta. Let's set it to 1 for now, and we will check for the key movements. So for left, right, and up and down, we will change the direction. We will change the value of offset x and offset y to move around the value. So if get key, these functions are provided by olcPixelGameEngine. So olc key left dot be held if the button is held. What we will do is we will reduce offset x by delta. Yeah, it's as simple as that, and we can paste it 4 times for left, for right, for up, and for bottom, or for down. And for up and down, this will be for y. For up, y will increase, and for down, y will increase, and for y down, y will increase, and for up, y will decrease, and for right, x will increase, and for left, x will decrease. And the same thing will be, and for the scale, we will use the mouse. So we will just say if mouse scroll wheel, we'll say if get mouse wheel, or something like that. I think this, if get mouse wheel, if this value is somehow greater than 0, that means we are scrolling up. We will just do the same thing, scale plus equals delta. And for the reverse situation, so if it's less than 0, then we will subtract delta from the scale. And now we can just draw the whole thing into the screen. So we will say, we will just do a for loop. So int y equals to 0, y is less than height y plus plus, and then for int x equals to 0, x is less than width x plus plus. And here, first of all, we will get the value from the noise, but for that, let's create 2 variables that takes our scale and our offset into account. So float x1 is equals to, let's say, x times scale plus offset x, like that, and we will divide it by width, sorry. And the same thing will be for y. So this will be y1 is equals to y times scale plus offset y. Okay, that being said, we can just query the noise now, and we will have a value for our color. So I will just call it v, and this will be our noise dot value, and for the value for x1 and y1 here. And then we can simply draw that pixel, like for that we will say draw, and we will pass the coordinates, that is x comma y, where we will draw in the screen, and we will set olcPixel, and we will use the v value for the red component, and the other components will be 0. So blue and green will be 0, and we will be looking everything as a red. So I think this is enough for the testing purpose. We can run this code now, and hopefully we will get some errors. We might not get some errors, but we can get some errors, and we got some errors. So first of all, gradients undeclared. So I did a little bit of debugging, and there were some simple issues. First of all, this will be std vector. I thought I declared std namespace globally, but I didn't. So this will be std vector. And the second thing is that the indexes of the gradients, they are used as ix. Okay, I extracted ix and iy for the indexes, but I actually used y and x instead of ix and iy. And the third mistake that I did, it was very trivial. The value of e is in between 0 and 1, but our the value of olc pixel goes between 0 to 255. So just multiply 255 here. So these three things, if you do, then we can run this application easily and look at our generated Perlin noise. And also I forgot to init the vector here. Just let me quickly show you here that you need to init the noise before you use. So as you can see here, a noise has been generated. So these four changes that I have done: first of all, I initted the noise. Second, this will be std vector instead of vector. The third is we will be using ix and iy, not x and y, because these are the integers and x and y, they are floats. And the fourth thing is we will multiply value with 255 to get the range changed. Now if we zoom this, you can see that we can easily zoom the Perlin noise here, and the more we zoom Perlin noise, the more it looks like actual noise. And we can also zoom in here like this, and here it looks a little bit dizzy. And we can also move around x-axis and move around y-axis easily. As you can see here, I am moving around x-axis and moving around y-axis, and everything is wrapping around. So now I hope you have understood how Perlin noise works and how we can easily implement Perlin noise in very little bit of code, like for using 80 lines of code. And we can use Perlin noise in our 3D applications or 2D applications, whatever we use, whatever or create. So thank you for everything. Hope you have enjoyed this video. If you feel that you have learned something new from this video or this video was helpful, please consider liking this video. It motivates me to make these kinds of videos. Thank you very much.